Welcome back, and we're going to continue our discussion on stereochemistry in this video and in successive videos as well. But before we get started on what we're going to learn now, let's recapture what we learned in the previous video. Right? In the previous video, or the entire video was dedicated to the idea of chirality. And what is chirality? Chirality is a property that is very much dedicated to carbon. Carbon is the only element on the periodic table that can have chirality. And how did we define chirality? Chirality is a carbon, okay, with 4 different groups, or let's write it as a carbon attached to 4 different groups. Now, it's not just the bond we're looking at, it's 4 different groups. And I like to summarize with an example. For instance, if this is what you have, okay, say this is what you have. Let's get a different color so we can. So as I've always told you, anything that is sticking out is a CH3, right? So if you draw it in line structures, okay, you don't need to do that, but I'm just showing it so you see what we are dealing with. And you can do the same if you feel you're still not comfortable with the line structures. Even though I might give you line structures, you can still convert them into, you know, your familiar carbon hydrogen skeleton, right? Now, if you notice, this is a CH3, a carbon. Well, technically a CH3 it's attached to 3 hydrogens, right? So it's attached to 3 hydrogens here, right? That means it can be chiral. It has to have 4 different things, right? While this whole thing is a different group, this carbon itself has 3 identical hydrogens, so that can be chiral. What about this? Well, this is a carbon. It's attached to a hydrogen, right? It's attached to the CH3 on one side, a CH3 on the other side, right? And then this whole group, right? CH2, CH3. Is this chiral? No, because this carbon is attached to a CH3 and it's also attached to a CH3. This carbon is attached to 2 hydrogens and then also attached to this methyl group on one side and this whole big group on the other side. So it's containing 2 identical groups. That's not chiral. And again, the same deal here. This carbon is attached to 3 hydrogens, and then it's also attached to, let me write the carbon here so you think you know that it is a carbon. And then it's attached to this whole group on the other side. Still, this is attached to 3 different groups. So none of the carbons on this particular compound are chiral, right? So what if we draw a different one? Let's get our blue again. I'm just recapturing, okay? I'm not teaching you something new. This is still part of the old material. What if I have something like this, right? As I said, these are all carbons, and any terminal carbon is always a CH3. So that's a CH3. This is also a CH3, right? This is a CH2. This is a CH3. And let me draw that in a different color. Okay, so this is same as writing CH3, CH2, CH3. And this is why I brought you all to learn how the bend works, how everything works before we got here, so that you have that primary knowledge on how to handle things when it's purely line structures. Right? So now if you notice, this carbon can be chiral. Well, it's got 3 identical things. This got at least 2, so neither of them are chiral. If you come to this one, if you come to the 3rd carbon, well, you see that it's attached to a hydrogen. It's attached to a CH3. On one end, you have this whole group. That's what I keep saying. You're not just looking at this bond right here between the CH and CH2. You're looking at everything that's attached on one side to this carbon. Similarly, this side is attached to this massive group, right, on the other side. And then you have the CH3 and then you have the hydrogen, right? So you have 4 different things attached to this carbon. So if we go back, then we can say this is chiral, right? And again, this is not chiral because this carbon is attached to 2 hydrogens. Of course, it is attached to 2 different groups on left and right, but on the carbon itself, remember, a carbon contains 4 bonds, simple. If they're all different, then yes, it's chiral. If not, it's not chiral. So there is only 1 chiral carbon in this entire molecule. Whether a compound contains 1 chiral or 2 chiral or 3 chiral, if it contains chiral carbon, the molecule is called a chiral compound, right? Right? So this is a chiral compound. Whether it contains 1 chiral carbon or multiple, it doesn't matter, it contains 1 at least. So this is a chiral compound and this is a chiral carbon. Those are 2 different things. Okay, very good. So now we are going to move on to something else, right? Okay, so what are we going to learn next is plane of symmetry. This is very, very important. Okay, plane of symmetry. Please do not confuse it with planar. Okay, this is plane of symmetry. It's not same as planar or not planar. Okay, these 2 are 2 different things. Please don't mix them up. Okay, is not same as planar or not planar. It's just a plane of symmetry. Now, typically a molecule with plane of symmetry is achiral, something we have not learned. What is achiral? It's just the opposite of being chiral, which means it's achiral. It's a term we have not learned, and that's why we're making this video, is we're going to learn one thing at a time, right? So a molecule with a plane of symmetry is typically achiral. Let's look at some examples. So let's look at this molecule. It doesn't have to be a cycle. It could just be a molecule that just has just a perfect plane of symmetry. Okay, I'm just gonna draw this carbon and then, okay. Now, if you look at it, okay, none of these carbons are chiral. This might seem to you at first that this might be chiral because I'm going to get my blue here. Okay, this carbon is attached to a hydrogen, a methyl, and this group on this side and this group on this side. At first it seems like visually, yeah, that could be a chiral carbon, but it is not, because they're exactly the same on both sides. So sometimes for molecules that are not cyclic, you can just say it is not chiral because there's not a single carbon here that has 4 different things attached to it, right? But this might seem like this is chiral, but it's not, because I'm going to show it right now with a different color, perhaps a pink. If you cut this molecule exactly in half, right along the middle of this, okay? If you cut it, imagine you just slice it right along that line where the CH3 is and cut it exactly half. It looks exactly the same, right? I mean, it would look something like this. I mean, this is part of the slice, right? This looks exactly the same on either side. So this is called a plane of symmetry. If you have a plane of symmetry, that means that molecule is chiral. The molecule is achiral. Sorry, the molecule is achiral. Okay, let's look at a couple more examples, because again, we don't need to dwell on this one particular topic forever. We just need to learn a few examples. Let's say we have this molecule, okay, and I have this. Visually, for some people, it's easy to identify chiral carbons when it's part of a straight chain compared to when it is in a cyclic ring, right? Now, this one actually has a hydrogen, right? And it's attached to OH, and it's also, this carbon is also attached to hydrogen and OH. The problem that they have is they often don't look at everything below. They just look at the bond. Oh yeah, it's the same. No, you just, when it is cyclic, if you can chop the molecule into exact two halves, well, if I run my blade right through the middle of this carbon into this carbon and run it straight through, what do you think is happening? Because no one, let me go back and erase this. See, there's no problem saying that there's OH and OH and a hydrogen, right? But the problem is, well, these look the same on both sides, these look the same on both sides. And that's what we mean by, if you can draw a plane of symmetry cutting these two carbons together, you'll notice that the molecule is exactly the same on both sides, right? Because to figure out what is this carbon is attached to, right? This attached to OH and a hydrogen, but then it looks exactly the same all the way down, okay? Everything, you don't just look at these two carbons here. You look at everything that is attached to this carbon. You don't just look at the immediate next ones, but you look at everything else. And if you see everything else is exactly the same, excluding this OH and the OH, because that's where we're cutting, it's exactly the same, this is a chiral. That is, it has a plane of symmetry. Let's look at some other one. Okay, let's draw a molecule that looks like this. Oops. I'm not very good at drawing my cyclohexane, at least not with this pen right here. Let's say I give you this molecule and I ask you to tell me if this molecule has a chiral center, and if you see there is no chiral center, then you say it's a chiral, right? And how do we know it's a chiral? At least is, okay, let's get a different color. Maybe a pink will work. This carbon cannot be chiral because it's attached to two, even though it's attached to this bulky group and then it's attached to a hydrogen, it still has two identical groups with our methyl and methyl. So that's not chiral. And the same deal for this one. This is also methyl, methyl. Let me move this out of the way. So that's also a methyl. And it's also got a hydrogen. So, but whether or not the remainder of this makes this a chiral is a question, right? Is this chiral? Well, because this whole group is, this is one whole group, right? I'm going to draw it. Okay. That's why I'm doing this particular example is I'm going to do a alternate version of the same compound. This is a completely different group. This one whole thing is a group, okay? When you are dealing with this carbon, okay? So, but the fact is it contains two methyls, so that's not chiral. Let's move on to this carbon, okay? This is attached to this whole thing, that's one. And then this also has a hydrogen, which is the second, right? So this whole thing is one group. And this is hydrogen. But the question is, well, this looks like it's identical. Well, what you can do is just do a plane of symmetry right through this carbon. If you notice, if I slice through this carbon into this carbon, this side, it looks exactly identical to this side. And which makes sense because we've already said that this carbon is not chiral, so is this. And if we can prove that whether this carbon is chiral or not through the plane of symmetry, which we find it's exactly the same everywhere, inch by inch is the same, whatever's on the left side is same as the right side. Okay, so this is again a chiral. Okay, So let's do another molecule on the screen itself since we have some space, and I'm actually going to use the same color. So let's use the red. So let's say we have this, okay? And then we have a double bond, and say we have a OH, and we have a OH here, and then say we have a OH here, okay? Clearly, let's get a different color again. So this is a carbon which is attached to a OH and also an hydrogen. So is this carbon, hydrogen, and a OH. It doesn't matter if you drew it on the right side or left side for convenience, and I don't want to get to the edge of my tablet, so I'm drawing it on this side. So still there's a question remaining, are these two identical? Well, clearly it's not. On this side of this carbon, right? So if I draw a line straight through this carbon into this carbon, right, to determine if these two ends are identical, right, clearly this side has a OH and this side doesn't, right? So that means these two groups attached to this carbon are different. So this carbon is a chiral carbon. This does not have a plane of symmetry. So is this carbon is attached to hydrogen and OH. This carbon is attached to this side, which doesn't have the OH. This side is also attached to this group right here, which contains the OH. So this carbon is also a chiral carbon, which is indicated by, so there's no, for this particular one, there's no plane of symmetry. So it is chiral. So typically a molecule that has a perfect plane of symmetry tends to be achiral, and a molecule that doesn't have a plane of symmetry typically is chiral. All right, so let's look at something else that we have not looked at, and I do want to bring that discussion up before I actually go further with something else, right? Let's say you have this, okay? Right, and I did bring this idea up earlier, and let's say Br and say, and I did mention this, and I think you do have to remember it. This means coming towards you, or towards you, coming towards you. Whatever element you have on there is coming towards you from the plane, whatever the plane is, it's coming towards you from the plane. And this typically means, okay, going away from you from the plane, okay? But if you remember coming towards you or going away from you, that's good enough. I mean, if you don't add the words from the plane, then that's okay. But as long as you know this, you're good, okay? Now, when typically in chemistry, at least in organic or stereochemistry, when you have two groups, okay, that are part of both pairs, or this, or when you have two groups that are attached to this pair or this pair, this corresponds to a cis. That is, let's say you have a Br and a Br, or a Br and a Br. Okay, if they are both part of either coming towards you or going away from you, if they're both in this, if they're both part of this, then that's a cis. Whereas say you have a compound that contains one Br that's coming towards you and the other Br that's going away from you, or any group for that matter, if you have two like groups, one is coming towards you, one is going away from you, that's a trance. If you have two groups where both groups, two identical groups, both are coming towards you or both are going away from you, then that's a cis. Now, if you notice, this is a chiral carbon, right? Right? Because this contains a methyl, and then it contains this Br, it also contains a hydrogen, and then it contains this whole group, right? So this is chiral, so is this. right? Because this contains a metal, and then it contains a Br, and then a hydrogen, and then it contains this whole group on the side, right? So this is chiral, right? Very good. Now, so this molecule contains 2 chiral carbons, and we can say that, well, it doesn't really matter where you number from. It's because it's very symmetrical. So I'm just going to go do from here. So if you number it, it'll be 2,4 dibromo pentane, right? Yeah, pentane. And then because these 2 groups are opposite to each other, as I said, if 2 like groups are opposite to each other, that is one going away from you, one coming towards you, that's a trans. So it's trans 2,4 dibromo pentane, right? And this is a chiral molecule because it contains 2 chiral carbons. As I said, whether it contains 1 or 10, if it contains a chiral carbon, it's a chiral molecule. Now, I might just violate the thing I just said in this special case, okay? Okay, in this special case. Oops. Okay, now this is a very, very special case, and if I say special case, chances are I might test you on that. Now, this carbon is chiral because it is attached to a Br, it's attached to a hydrogen, it's attached to a metal, and it's attached to this giant group, right? I keep repeating, it's not just the bond attached to this carbon, it's the whole thing. And so is this, it's also chiral because guess what? It's attached to a bromine, a hydrogen, a metal, and this group on the side. But this molecule itself is achiral. Well, the name is going to be the same. So it's 2,4 dibromo pentane. The name doesn't change. There's 2 things that do change. Okay, one is these 2 groups are both coming towards you. So it's a cis and this is a trans. And despite the fact that this molecule contains a chiral carbons, plural chiral carbons, this molecule is achiral. You all probably figured why I'm saying that. This molecule is achiral. Why is that? Well, didn't he say that all molecules that contains a chiral carbon is a chiral molecule? Yes, that is true. But we're also talking about plane of symmetry. This molecule has a plane of symmetry running right between, and if you chop it, they're exactly the same. Because these groups are both coming towards you. And in the other case, if you take a mirror image of this, well, this Br will come here, this Br would go here, right? So you have a difference. If you cannot spot a difference in your mirror images, that means it has a plane of symmetry. Like if you close your eye and then I divide this molecule into 2, and then I flip them and then I reattach them, you can't really tell what I did. It'll turn out to be the same. What I'm saying is if I cut it right in the middle, okay, put the right piece in the left side, put the left piece on the right side and attach them exactly the way they are, it's still going to be looking exactly the same because there will be no difference to your eye. Your eye can't pick up that difference that the molecule has been cut and reunited. You can't tell. Whereas if I do that same thing here, okay, if I cut this molecule right here, okay, or take a mirror image of like right here, well, this would come here, this would go here. Your eye can tell, yeah, it was on this side, it's gone here now. What I'm saying here is if I take a mirror image, the Br would probably come to this side now, okay, and then I'm going to erase this, okay, and then say the Br was here, right? And if I take a mirror image, the Br would now be here, right? Your eye can definitely pick up that difference. You can tell this was on the left side, now it's on the right, This was on the right side, now it's on the left. Your eye can tell the difference. That's why there is no plane of symmetry here. No plane of symmetry, because one BR is coming towards you, one is going away from you. Typically, trans molecules don't have a plane of symmetry. Typically, cis molecules have a plane of symmetry. Something I want you to know, because if you don't understand this concept right now, then you're more likely going to have trouble gathering some of the concepts later. All right, so I'm going to stop this video right here, because this video I purely wanted to dedicate it to plane of symmetry, from just figuring out a chiral center or a chiral molecule. Okay, a molecule could have chiral carbons, but it would still turn out to be achiral because it has a plane of symmetry, just like what we did here. This is a classic case. I'm going to write the word classic example, where the molecule itself contains chiral carbons, but because the molecule has a perfect plane of symmetry that everything looks the same on both sides, guess what? It's going to be achiral. Okay, so when I give you these questions, think from both perspectives before answering. Now, you're not going to be answering 20 of these on a test, probably one problem. So take your time with the problem. If there are chiral carbons, first assign them and then look for plane of symmetry. That's usually the easiest way to do it, is first go look for if there's chiral carbons. Well, if it doesn't have chiral carbons, then I might still ask you the question, does the molecule has a plane of symmetry? You just have to say yes or no. I won't ask you if it's chiral or achiral at that point. Typically, if a molecule doesn't have chiral carbons, but it also contains a plane of symmetry, it's a double whammy that it is achiral. But a presence of chiral carbon itself does not mean that the molecule is achiral, because it could still fail under the plane of symmetry rule, where if it has chiral carbons but it contains a plane of symmetry, it becomes achiral. That's the point I really want to drive across. And then also I want to remind you what this coming towards you and going away from you is. I'm going to show you a couple of actually ball and stick models in class that'll maybe help you see this through even better. But for now, that's the point I want to get across in this video. And in the second video, in the third video, we're going to learn about R and S isomers, or R and I stereoisomers in the next video. So stay tuned.